So we are going to come to the flap and जो हम last time we had we did uncertainty relation, statement of uncertainty relation in terms of commutators. That two commuting operators, the measurement of two commuting operators is not sharp. That was the definition of uncertainty principle. So in this today's class, we are going to take an example of harmonic oscillator. जो हम तक करते आए हैं harmonic oscillator, but in the context of a linear harmonic oscillator, but in the context of a taking it as a quantum particle. उसकी ground state होती है, and we have degeneration states. जो energy eigen states के along that ground state, so along some stable minimum condition. Showed the equation, it was a stable minimum. So we had equation around. So first few orders in the Taylor's expansion. So then you correspond to those energy eigenstates, and मतलब इसका ground state in quantum particle, it was not exactly zero. It was 1/2 h omega. Linear harmonic oscillator का ground state zero आता था. It was not exactly zero for quantum mechanical particle. It was to be 1/2 h omega plus something. ऐसे. Normally is going to n h omega. ऐसे आ रहा है. N plus half h omega. So even though n is zero, so it will be also h omega by 2. For 1 it will be 3/2, 5/2, 7/2, so on and so forth. So for a given eigenstate, what will be the given eigenvalue? अब ये है कि how we can sort of so we have, for example, जो हमारे पास traditional methods हैं to deal with it. So जो हमारे algebraic processes we have done bracket formalism या operator formalism, उसमें हम इस harmonic oscillator को कैसे represent करेंगे? So traditionally हमारे पास tools हैं, जैसे differential equations के tools हैं, special functions है ना, special functions भी हमें क्या ना particularly Hermite function, generating function of Hermite polynomial that was shown in terms of psi, उसकी different values. So you can have this, or you can have integral representation. So these are more traditional ways of we have been doing it.
You can also do Green's functions.
Okay. There are the point is showing you different ways of doing the same thing. अब यहाँ पर हमारे पास जो अभी recently we had facility with bracket notation, bracket formalism. उसमें हम उस harmonic oscillator को कैसे representation देंगे, such that it will be जो ground states, higher states, next order states को कैसे represent करेंगे in bracket formalism. That's our exercise. So अब जो for example जो हमारे पास generalized so these methods are also as much viable, but here we are going to use generalized linear harmonic oscillator using harmonic oscillator. Linear harmonic oscillator बहुत important है physics में. एक फिजिसिस्ट है, उसका नाम है सिडनी कोलमैन, सुना है ना? उसकी भी एक बुक है
TFT के lectures है.
हाँ नहीं, उसकी एक बुक है सिमेट्री, बहुत अच्छी बुक है, ठीक है? उसमें उसका कोट है होल फिजिक्स इज बेसिकली स्टडीइंग लीनियर हार्मोनिक ऑसिलेटर, ठीक है? लीनियर हार्मोनिक ऑसिलेटर का ये है एनालॉजी दैट बिकम्स नॉट ओनली क्लासिकल मैकेनिक्स, वही एग्जांपल हम क्वांटम मैकेनिक्स में लेते हैं.
Apart from the European.
हाँ, apart from the So to emphasize the linear harmonic oscillator, this example has been very much important in the subject of physics, in the application of subject of physics. So अगर हमारे पास generalized linear harmonic oscillator है उसका Hamiltonian can be expressed in terms of observables P and Q, canonical observables. So Hamiltonian जो होगा it can be written as P square by 2m plus 1 by 2 m omega square whole square. ठीक है? और now here we are going to reparameterize it in terms of जो हमारी in terms of we are going to introduce Hermitian thing, iota thing here. So we can अगर m omega square by 2 को बाहर निकालेंगे तो we can write it like this. आप देखो q plus iota p by m omega and q minus iota p by m omega minus h omega by 2. h omega means वो 0 point energy है. ये क्या है? अब देखो इसको आप स्क्वायर करेंगे, a स्क्वायर माइनस b स्क्वायर आएगा, यहाँ q स्क्वायर आएगा. तो ये फर्स्ट टर्म आएगी हमारे पास 1 by 2 m स्क्वायर ओमेगा स्क्वायर q स्क्वायर. दिस इज बेसिकली a स्क्वायर माइनस b स्क्वायर. ये आएगा दूसरी वाली टर्म क्या है? माइनस आयोटा स्क्वायर p स्क्वायर बाय m स्क्वायर ओमेगा स्क्वायर. माइनस आयोटा स्क्वायर आएगा प्लस 1 p स्क्वायर बाय m स्क्वायर ओमेगा स्क्वायर. m m कैंसिल हो जाएगा, तो ये m नीचे रहेगा. You can reproduce and it's the 0 point thing. तो अब हमारे पास जो Hermitian प्रॉपर्टी है, Hermitian ऑपरेटर्स हैं, they satisfy commutative relations. P2 minus Q, P is not necessarily 0, so it's some iota h cross phi. And both P and Q can be continuous spectra, means extending from minus infinity to plus infinity. Means कोई भी वैल्यू ले सकते हैं यहाँ से भी, range of the values can be anything. Now what we are going to do, we are going to consider the eigenvalue problem. Eigenvalue problem of H. अब हम करेंगे काम, A को डिफाइन करेंगे such that so it will give us a destination. So we will convert a new operator को define करेंगे. A is defined as an operator is defined as m omega by 2h q plus iota p by m. A as an operator would define it like this. ठीक है? To introduce operator formalism, A को हम ऐसे डिफाइन करेंगे. तो A अगर क्या आएगा इसका पर? इसका कंजुगेट. If you define A like this, A diagram, तो ये iota P है, ये क्या आएगा? इसका Hermitian कंजुगेट आएगा डायग्राम में. माइनस iota. Now, जो Hamiltonian हमारे पास आएगा, it will be आप A डायग्राम को मल्टीप्लाई करो, it will come out back this, है ना? If you multiply it, A को A के साथ मल्टीप्लाई करो, तो H will be A डायग्राम A अगर मल्टीप्लाई करोगे, it will be you can easily prove, it can easily be shown that it's A diagram. So A डायरेक्ट को आप मल्टीप्लाई करो तो इट विल बी q स्क्वायर माइनस p स्क्वायर बाय 2. So you can see Hamiltonian move as A and A. So A को ऐसे रिप्रेजेंट करो, इसको A diagram is this. This is second term. This is first term. So you can write the Hamiltonian like this. Or if we want to, या अगर हम उसका again, so if you can, you have always be clear. So we'll इसको यहाँ रखेंगे, इसको यहाँ लेंगे. A then शाबाश।
Convention
This is this plus or minus. It will be minus. Okay. इसका यहाँ रखेंगे इसका। Now where A diagram is Hermitian adjoint of A. अब what we are going to do? A diagram A minus A this is another exercise. This is I or this is one. Yeah, I will tell. अब ये exercise आपको आप पहले A को A diagram के साथ मल्टीप्लाई करो, then A diagram को A के साथ मल्टीप्लाई करो. So it will not come out to be 0. So you do this exercise 1 minute. Since we are not much time left. So this is the thing. This is the exercise. Since H is a linear, by 10.70, 10.70 means 10.70 is this. Since H is a linear function of A, H is a linear function of A diagram E. The eigenvectors of H eigenvectors of H and A diagram E are same. इसका मतलब क्या है? मतलब eigenvectors जैसे eigenstates are being acted upon by operators, they will do eigenvectors. Since ये same है, so they will be same. Now, just directly. So expressing eigenvalues lambda n is equal to 1, 0, 1, 2, n is equal to 0, 1, 2, so on and so forth. So corresponding to, so for n eigenvectors, this can be the eigenspace side. So अब अगर हमारे पास left hand side में A diagram A है, which is operating on psi n, it will give us lambda n psi. This operating on this will give us different values of n's. 1, 2, 3 जो भी हमारे पास. अब हमारे पास if you remember linear जो है operators, you just go back इसी बुक में जाओ या कहीं पर जाओ, इस बुक में is better. When we try to study properties, जो inner product की properties क्या है, multiplication by linearity property क्या है, inner scalar property, when you multiply inner product by scalar तो scalar बाहर आता है. So you are going to use for lambda n greater than 0. So one of the property is like this: psi of n, if it's multiplied A diagram A, psi of n. Can since very good. Psi of this is A diagram A, so it will correspond to this. So it can be this. You can replace it by lambda n. So lambda n बाहर है. Sin, or it's or A of or A of psi and psi. A psi. So it will be lambda and psi and psi. So how scalar will come out? We'll do it. But for lambda n greater than or equal to 0, we conclude if n is the eigenvector, if n is eigenvector of A dagger A, if n is an eigenvector of A dagger, हम क्या कहते हैं यहाँ पर? Each operator acting on state psi, it will give an eigenvector. So eigenvector can be same or different. ठीक है? So normally, no, it will be same for a given. Different states will have the same eigenvectors. Okay? So for orthogonal, it's easy to find. For orthonormal, so if it is like that, and A dagger n is also an eigenvector, which can be seen as, अब देखो यहाँ पर हम करेंगे काम वर्ग टू सबस्टिट्यूट जो ये है यहाँ पर ये देखो A dagger A है this A dagger A here A dagger A is equal to A dagger A plus 1 या है ना A dagger A is equal to A dagger A plus 1 इसको हम सबस्टिट्यूट करेंगे यहाँ पर so A dagger A if n is an eigenvector of A dagger A and A dagger n, so A dagger n, so अब हमारे पास दो आएंगे A dagger A and A dagger acting on n. So इस A dagger के बदले हम लिखेंगे A dagger A plus 1. So it will be A dagger A plus 1 into n. And this will be equal to the upper lambda हमारे पास आएगा. But here it's lambda n plus 1. The point to show is that है ना आइगन स्टेट्स या आइगन वैल्यूज n वैल्यू है n plus 1 n plus 2 या n minus 1 n minus 2 n minus 3. So the suitable application of operators on these eigenstates, how we can get the next order eigenstates, in the both ascending as well as descending orders of expansion. ठीक है? By this simple exercise. हमने कुछ नहीं किया, पहले ये प्रॉपर्टी यूज की, फिर A dagger A को हमने एज एन ऑपरेटर लिया, फिर ऑलरेडी हमारे पास ये, फिर इससे यहाँ से ये निकला n plus 1. बट इसका ये रिप्रेजेंटेशन A plus 1 है, तो यहाँ हमारे पास आइगन वैल्यू आएगा लैम्डा n plus 1. ठीक है? अगर A n plus 2 आएगा तो यहाँ आएगा लैम्डा n plus 2. अब n minus 1 आएगा तो लैम्डा n minus 1. ठीक है? So that's so on. So इसी को हम कहेंगे कि it will be lambda n plus 1 or it will be lambda n minus 1. इसी को हम कहते हैं, फॉर एग्जाम्पल if they are justified by designation, A dagger को हम कहते हैं raising operator, and A as lowering operator. So by applying these operators, we can generate a given eigenvector. इसी को हम कहते हैं a procedure which is also known as ladder operator method. You have an eigen operator operating on state that will be a particular eigenstate. जो next order है ना, continuous tower of states. Ground state which आप excitation करते हैं ठक कोई state raise होती है, next excitation next state. Given eigenstate psi operated upon by operator, it will give eigenstate. उसका continuously, it can go for ascending as well as also descending
What
also.
allows us to do is the fact that commutator is identity.
हाँ ना ये है ना ये हमारे को निकाला ना ये this is a normally it comes out to be 0. A dagger a minus a dagger normally commutator है ना commutator ये है it comes out to be 0. वही तो है ना uncertainty yesterday's class. So it will not come out to be 0. It will come out to be some complex number है जो उसको use करते हुए we can just define the quantum state which is different from the classical state. Classical state it will come out to be 0. Since it doesn't come out to be 0, so we are able to show the transitions from ground state, next state, next to. So this is the way we construct states. Such that अगर हमारे पास so maybe next when you study advanced quantum mechanics, this is here we have only a feeling कैसे करते हैं. Here we will more rigorously. So by letting n is equal to 0, अगर ground state में 0 होगा तो ये होगा lambda 0. We talked of lambda n, we don't talk of ground state. So 1 is greater than lambda is greater than 0. Or a acting on ground state is 0. There I lambda I value is 0. So starting from 0, all eigenvalues by repeated application of the raising operator. हाँ अब इसमें ये है कि we can now use for n and rather than saying 1 हम जो a dagger है जो स्टेट को रेज करती है a dagger for all states we are not going to इसका ऊपर एक्सप्रेशन करेंगे n which is acting upon ground state. So ground state classically 0 है यहाँ से ground state का भी कुछ वैल्यू है. So that's why we start from something. Fine this. So ground state पे भी 0 नहीं आएगा कुछ आएगा है ना. So ground state a and 1 it acts on कुछ देगा 2 पे n plus 1 3 पे n plus 2 ऐसे करते करते state for 0, 1, 2, so on and so forth. For lambda is equal to n. So normalization n must be determined. There is no general there is no degeneracy as long as we can write there is no degeneracy. इसका मतलब क्या है? There is no degeneracy as long as no dimensional variables P and Q characterize the system. इसका मतलब क्या है? There is no degeneracy. So degeneracy means all different states will have a unique eigenvalue. Different states will have. So there is no degeneracy as long as no dimensional variables. If they don't characterize, if they are not dimensional variables, there is no degeneracy. So it's simple. So now इसी चीज को हम generally कैसे लिखेंगे? H so H Hamiltonian is acting on this state है ना. Schrödinger equation में लास्ट में क्या कहते हैं? H psi is equal to E psi. Hamiltonian operator left side is equal to so H this acting on this state will give us H omega. This is energy state. N plus 1 by 2 n. So H operating on n state तो ये continuous state देगा 1, 2, 3 so continuously जो operators succeeding और जो भी है both sides you can see और eigenvalues of the Hamiltonian वो होगी E n is equal to H omega 1 by 2 ये आएगा n sorry E n is equal to H omega n plus half. So this was a simple exercise, but it's a very important and very example. How you can generate states, eigenstates from the application of operators on a given eigenstate which will give different eigenvalues. Okay? And starting from the ground state, which is not in quantum state. This doesn't exactly coincide there. How it is a procedure, which is called ladder method with that, operator method with that. So next, so I'll just this exercise of substitute 10.9. I recommend you to see it at your place at least. What are the eigenvalues of kinetic and potential energy operators of a Hamiltonian oscillator? Explain why they don't add up to discrete energy values of the total energy. Okay, so this is an exercise which is shown. So you at least read it. Since you don't have time, otherwise. What are the eigenvalues of kinetic and potential energy operators of harmonic oscillator? इसकी kinetic and potential energy क्या है? Explain why they don't add up. So, and the subsequent exercise 10.9 and 10.10. So exercise 10.9 and 10.10. Okay. So I can ask you exam. Yeah. More up just read it. If you have some difficulty, you can ask. Okay.